morning, students. So this class we'll be discussing about MOSFET. So MOSFET is one of the FETs, one of the types of field effect transistors. So among them we'll be seeing MOSFET. What is MOSFET? MOSFET is metal oxide semiconductor field effect transistor. So this is how the basic structure of MOSFET looks like. So this is MOSFET has a source, a gate, and a drain, right? So here it also can have two types. So it can either be an N-type MOSFET or a P-type MOSFET. So do you find any similarity to the previous chapters or the units that when we discussed either the BJTs or the PN junctions? So do you find any similarities for a phenomena that we have discussed before? Can look it a little more carefully. So I'll leave you a little more time to think about it. So in next slides we'll discuss about what it is. So here it basically has so this is how a schematic of a MOSFET looks like. So here we have a substrate and which is a silicon substrate. Based on that there is the channel base. So above which a source, gate and a drain are fixed. And there is also an oxide layer or an insulating layer between the gate and the channel base. So there is an insulating layer here. This is there just in the gate section. It's not there in the source or the drain. So that we can observe in the foremost figure. And another is also another schematic where it shows the dimensions like L will be the, we'll discuss about this parameter L later, right? And D is the thickness and W is the width of the MOSFET system. So we'll discuss in detail about all these parameters and have in mind this question about what is the similarity in the chapter. I can give you a clue that it is related to the PN junction diodes that what we have discussed before. So you can have a recall of what is this similar to. Okay, so normally the gate channel insulator is made out of a dielectric material. So dielectric material is silicon is semiconductor, but when we oxidize it, it becomes a dielectric, and the dielectric parameter is given by the number 3.9. This is how it is. So now this is how a basic MOSFET. As I said, there are two types. One is the N-type and another is a P-type. So for understanding the physics or the principles behind or the mechanisms of conduction, we have taken an N-type MOSFET device here, right? So what does this N-type mean? This N will be the base channel, or the N material will be the base channel which will be housing the source, the drain and the gate. The gate will anyway have an insulating layer, but this will be the base channel without. So all this will be the N-type material. So that is what will make a MOSFET as an N-channel MOSFET. So if you want to make a P-channel MOSFET, you can automatically think that instead of having a N-type channel base, we'll be having a P-type channel base. So that is what is the difference. And below which there will be another N-type material or a P-type material depending upon what is our channel base. Okay, right. As I said here, so the gate has a very thin insulating layer. Now can you recall it? I guess some of you would have gone, or I hope that most of you get across it. It is similar to the Schottky barrier that what we discussed in our PN junction diode. So what is a Schottky barrier? Schottky barrier is something that, yeah, can you recall? So Schottky barrier is something that it helps us to lower the cut-in voltage, right? We can define the cut-in voltage using that. So that is what the Schottky barrier is for. So look into your previous notes before, right? So here, so below the gate there is this insulating layer just below the gate. So the source and the drain are directly connected to the channel base, so which is the N-type channel base here. Suppose when we give a positive voltage, what will happen? It will push away all the holes that are there in the P-type material, and it will attract the movable electrons from the N region, so under the source and the drain. So this is what will happen, right? Are we getting it clear? So if we give a positive voltage to the gate, so the voltage is given where? To the gate. So when we give that, because it's an insulating base, it has a non-insulating base, it's a dielectric medium. So this will push away the holes inside the p substrate, and it will attract the movable electrons from the n region under the source and the drain. So basically, when we give a positive voltage to the gate, it will attract the electrons from the n region that are under the movable electrons under the source and the drain. So this is how it works. There are two modes at which it can work. One is the enhancement mode and the normal mode. So the enhancement mode is nothing but the amount of current that what we give to the source, the amount of the current which can go from the source to the drain will define a transistor to be in an enhancement mode, which is nothing but increasing the positive gate voltage. So by increasing the amount of the voltage that we give to the gate, we can change the transistor mode into a enhancement mode. So thereby the thickness, it enlarges the thickness of the channel created. So what is this channel? Where is this channel created? So we'll discuss all these things a little briefly. So this is what happens in an n-type channel. So this is a schematic, again a schematic of a MOSFET here. So you can see here there are output voltages drawn across all the three junctions and between junctions also. So the VGS is nothing but the gate source voltage, and VDS is the drain source voltage, and BS is it's a back contact. So between the back contact and the source. So these are all the three voltages that we'll be interested in, and this is a symbolic representation of how a MOSFET is represented by. So we'll have three zones, which is nothing but the gate, drain, and the source, and then there is also a substrate current and the direction. So representing that, this is an n-type MOSFET. So as I said, p-type, this is very complementary to that of that. So instead of having the base channel as n-type, we'll have this as a p-type. So that is the only difference. And similarly, the voltage that what we'll be giving to the gate will be not a positive voltage but will be a negative voltage, so that it pulls out all the holes that are immediately beyond the drain and the source towards the gate, and thereby enhancing the performance of the transistor. Right? So you have any doubts until so far? I'll just give you a quick couple of minutes to recall whatever we have discussed. Yeah, one more thing, the basic difference between this MOSFET and the n-type MOSFET and the p-type MOSFET is that the carriers that are moving. So for example, in n-type it will be electrons, and in p-type we know that it's the holes. This is another a very prominent or a very basic difference between them. So the next we'll look into the structure, principle and operation of this MOSFET devices. So this is how a top view of it looks like. We have already discussed what is VDS, what is VGS, and IG is nothing but the current or the gate current that is entering to the gate, and ID is the drain current. Okay, this is the, and L doesn't mean here literally the distance between the drain and the source. Sorry, doesn't mean the gate length. It means the underlying layers between the gate, right? This is the top view. So now we have to imagine that we have to compare it with the previous slides before, right? So where beneath the gate there is the insulating layer, and then only on the channel layers where the source and the drain are placed. So what will be the distance between the source and drain is called as, that is given by this quantity L, and W is the width of this gate, right? So here we have introduced two more parameters, and what will be the importance of this, we'll all see it in detail. So here in this basic, we were talking about the channel width, right, and the channel and all those things in the previous slides. So here the channel width will correspond to your interaction between the acceptor and the donor level interactions between the n-type and the p-type material. So that is how the electrons or the holes can be pulled from one one part of the from the n-type material to the p-type or p-type to the n-type material. So this is just a schematic of showing what is happening. So all these things are happening uh, at this gate point, right? So this is why the distance between the or the length between the source and the drain becomes so important. So that helps us to have this interaction. And we will be also seeing about three terminal devices. So that are this is a three terminal device, right? Why? Because it has a source, drain and a gate. So VG is nothing but the voltage at the gate. So when that is zero, the source, the drain current and the drain current is zero. But when the gate current is less than zero, which means when the gate current is negative, the drain is zero. But when the gate current is greater, then the drain current is also large enough. So the gate is the so this device is a gate controlled device. So where the potential barrier here between the N type and the P type plays a role, or it's a resistor. So this gate is the controller for whole of this MOSFET device. Either it's a P or an N type. This is how the IV characteristics of a MOSFET looks like, right? So in the first case is for a low drain voltage, and the second is the onset of a saturation point. The saturation point P indicates the pitch off point, and after that the C section indicates it's beyond the saturation. So these are the three cases that's what are discussed. And simultaneously we can also see in the schematic of what is happening to the length. For example, in the initial case, the length L, right? So that is there where it is a low drain voltage. But when it hits off to pitch off, the value of L varies here, right? So it really comes down. And when we talk about beyond saturation, the value of L drastically comes off. So this is again the ideal output characteristics of the MOSFET. So for output, we'll be studying between ID and VD, where there is similar to what we have discussed in the previous, right? So where there is a low drain voltage, and then there is a pitch off, and then finally a saturation happens. So this is how it should look like, an ideal saturation curve. So these are all the different output characteristics for different types of MOSFETs. So on MOS and different working conditions. For example, in a normally off condition, so this is how the output characteristics looks like. So with the values, right? When it is in the enhancement mode, the values are higher compared to that of in the depletion region. Like in the depletion region, we see that it's in a negative, whereas in the enhancement mode, it is higher. The drain current is higher. And similarly, in p-type material, all the values of ID what we get is in the fourth quadrant, meaning that the value of the VD is negative here. Will not be interested in transfer characteristics. So again here another semantic of showing the different modes can also be represented using schematics. So here for an N channel, depletion mode and also the enhancement mode is shown, and similarly for the P channel. Here you can see when the current directions are seen towards gate, it's an N type. When it is away from gate, it is a P type. Here you can clearly see the difference. Can you also spot out how is the depletion and the enhancement layer differentiated? Can anyone? The way how the source and the gate are all connected, you see that source is directly connected, like the arrow that goes, so it's three different dotted lines, right? For the drain, gate and the source, and we also have a small line, whereas in the depletion region we just have one long line. So that is the difference you can clearly see here. So another here talking about the channel length and what should be the effective channel length. This channel length will also be a controlling parameter for us to see how the IV characteristics can be controlled, or what is the required voltage or the current requirements for a specific condition or a specific circuit that what you want to decide. So all this can be uh, monitored or controlled using the L and the W parameters. Similarly, power supply voltage. So when we want to scale down the MOSFET channel length, the supply voltage VDD must be reduced also to keep the power in reasonable limits. So this VDD parameter will tell us what can be the power of this MOSFET, right? So what is the good operating condition of the MOSFET? That is defined by this parameter VDD. Threshold value. So what is this threshold voltage? So threshold voltage is that below which voltage the transistor performance is in safe conditions, or the system is reacting to whatever the predicted VI conditions that what we have studied. So for this, the ideal oxide threshold voltage for the N channel is given by this terminology. So we'll just understand the physics. We'll leave off the equation. So these factors can change the threshold voltage. One is the body effect or the substrate base, right? And the second is the drain induced barrier lowering. So which is nothing but VDS and VB. So which is nothing but the base contact, right? So the base contact, the voltage at the base contact, and the drain source voltage. So drain source voltage and the voltage at the base contact play a major role in monitoring the threshold voltage, and this is also in collaboration, or in you have to understand it similar, keeping the threshold voltage of the oxide layer that is used, right? So again, the pitch of voltage is determined by also the oxide layer. So if the supply of the VDD is reduced in a constant electric field, the gate oxide thickness must also be reduced. So what is the use here? So by reducing the gate oxide, we are also setting up tunneling to happen here, right? Through the gate oxide current. So now do you understand what is this gate oxide current? So it is this insulating layer that is present beneath the gate. So this thickness also plays a prominent role in controlling the or determining the voltage current characteristics. So I think with this we'll wind up today's session. So where we have discussed what is MOSFET, different types of MOSFET, and what are all the different terminals we have, and what are all the different voltages that we are interested, the different types of MOSFET, and also the VI characteristics in detail. And we have also seen like geometrically what should be the width, the length, and also the thickness of these oxide layers and the material parameters. So all those things. So this has given us a good review of the metal oxide semiconductor field effect transistors. So I let you to think about this topic, and we'll you start preparing your notes based on this, right? So where you'll prepare a review for this MOSFET for whatever we have discussed, and you write your own notes, and I have also given you book information, so you have that as also a PDF format. So concurrently refer this with the book what you have, and then prepare a notes. So that notes will be a review. So you will not give a detail about everything that is there in this chapter, but you will point out the key factors that is there. So this will be presented as assignment. So this is the assignment for today. So if you have any doubts, you can post the questions. Like we can form a forum, and then we can share there, right? So we'll share. You can share the thoughts of how it goes. We can see ways to optimize it. So good luck in today's session ends now. Thank you.